the activated sludge process. Well, this is more or less the content of this presentation. Have you already heard about the activated sludge process in the previous lectures? Yeah, a little bit. So first, some about the setup of the process. So how does it look like in practice? Some process parameters, dimensioning, which means designing how big it should be, these kind of things. Oxygen supply, because that's the basics of the activated sludge process, that oxygen is needed. So there's aeration, and there are different systems, and clarification is very important, because the activated sludge process is based on a suspension of activated sludge bacteria, and these bacteria need to be separated from the water, the treated water. That's why the final clarification is a crucial part of it. So this is a typical layout. Yeah, just long enough. And this is weird. Here. That's not my drawing. It's not my scheme. And I would say this is wrong. It's not wise. Why? Do you have an idea what this is? That's the activated sludge process. By the way, activated sludge process it's somewhat less than 100 years ago that this was discovered by two British guys. They discovered that if you fill a reactor with wastewater and then aerate it for a while, then if you let it settle, there was some sludge, and they knew there was some sludge in the wastewater, and they called it sludge. And then they took off the supernatant, that was the clean water, and then discovered that after a short while, after a few times, this water became clearer, more clear, and so they discovered that in fact it treated the water. And they thought, well, this sludge which came with the wastewater was activated somehow. That was a mysterious phenomenon they didn't really understand, but like activated carbon, that was more or less comparable. So some way, somehow it became more active and it was able to treat the water. That's why they called it activated sludge. Sometime later, they discovered that it were bacteria that were growing in the sludge and making the sludge more active. It was in fact the bacteria that were active. It was not the sludge that came with the wastewater that was active, but the sludge that grew in the system. Well, this is, well, it's just too short, but this is a pre-sedimentation, so that's garbage. Will be collected here and separated from the settler. This is the activated sludge reactor. That's aerated, and this is the sedimentation tank. And the sludge that grows in the system is back to. It should be fed back to the reactor, but in this drawing, it's fed back to the primary treatment system. Also, for one part to the activated sludge reactor. But in reality, in most cases, it's like this. Activated sludge reactor, sedimentation tank, return to the aeration tank, and then, of course, there's the primary settler. And this is two types of sludge that's wasted. Yeah, so this is primary sludge without active bacteria, and this is secondary with active bacteria. It's different material. So, and it doesn't make sense to feed this back to this primary settling tank. So this is the waste sludge. What's important in the activated sludge process is a couple of things. It's a pity that this is pretty high. I need a longer stick next time. Well, the food, what they call, it's more or less the American literature where it's called food to microorganism ratio. So you can imagine in this process, you have a certain amount of microorganisms that grow, and the food for these microorganisms, that's the waste in the activated sludge, in the wastewater. And well, it depends on how much food you apply to the microorganisms, how active the process will be, and how fast it will run. So that's why we talk about food to microorganisms as a load, how much it's loaded with food, with wastewater. And for designing treatment plants, we talk about sludge load, which is a little bit different in many cases. The sludge load, as you can see, is the concentration of the wastewater expressed in, do you know? How do we express the concentration of waste? No idea? Chemical oxygen demand or biological oxygen demand. COD or BOD. That's the concentration. It's a sum parameter. This is looking to the biological degradable material, and this is the chemically oxidizable material in the wastewater. Anyway, so this is the concentration of waste. So that's S. And this is Q, that's the flow rate, and we have divided by the volume times X. And X is the concentration of sludge, of bacteria. So if we look at S, S is expressed in kilograms biological oxygen demand per cubic meter. It's a concentration. Q is expressed in cubic meter per day. Volume is expressed in nobody knows. Cubic meter, of course. And what about sludge concentration? Bacteria concentration. Can we express bacteria in a concentration? That's going to be difficult, right? Yeah. So that's also a sum parameter expressed as kilogram suspended solids. So that's the solids in the activated sludge per cubic meter. Okay, so if you look at the units of the sludge load, the symbol is BX, also LX. There are several ways to express the sludge load. Then we see that this is expressed in kilograms of COD per kilogram of suspended solids, which is a measure of the bacteria concentration per day, per unit of time. So if you look at this, you realize what it means. So it says how much we can treat per unit of bacteria per unit of time. Now that's a very important design parameter of the activated sludge process. So for design, we look at design values, and in this case it's expressed slightly different, but basically it's the same. It's in kilogram dry solids, but that's what we also call suspended solids. And well, you see this sludge load can have several values, of course, and when it's very small, we intend to, so there's a lot of bacteria, and a little pollution, food for the microorganisms, so they have to compete for the food. So they will do a very good job, in fact, because they will eat all there is. So that's why the effluent concentration, the treated water here, is low in terms of milligrams of BUD per liter. If we increase the sludge load, then of course it's doing a less good job. If at very high loaded sludge loads, as you can see 1 to 3, which is considered high, then the effluent concentration will be higher. So it won't do such a good job anymore. But sometimes we don't need to treat till very low values. Also, are you familiar already with nitrification, nutrient removal, nitrifiers? Not yet. Yeah? Ammonium oxidizers. Well, anyway, if you want to remove BUD and if you want to remove nitrogen, oxidize ammonia, then you need to grow nitrifiers, different organisms. And when the sludge loading is high, these organisms won't grow. I'll come back to this in the next lecture. So you can't have too high. So if you want nitrification, the sludge loading is always lower than without nitrification. Clear so far? Yeah, so this is just summarizing the importance of sludge load. It has an impact on the treatment efficiency, on the sludge growth as well, the sludge age, I'll come back to this, the degree of stabilization of the sludge, and nitrification, denitrification, whether this is possible or not, and also the oxygen demand. You can imagine, you could ask why not treat at low, very low sludge loadings so to have the best result. Well, if you treat at low sludge loadings, you need to aerate a lot. And aeration, that's 75% of the energy costs of a treatment plant, which is a lot. It's a big bill every year. So that's a reason not to use low sludge loads all the time. This shows some microbial kinetics. If you would, again, for example, you could do this in a similar way as I showed before, the way the two British did 100 years ago, fill a reactor with activated sludge and wastewater. So from the beginning, there will be, if we look at the substrate, the blue line, for example, that's the waste. In the beginning, the waste concentration is high, and then after a while, this is the time, after a while it will decrease until it reaches 0 or almost 0. It will reach a low value. At the same time, in this reactor, because of food, the microorganisms, the bacteria, will grow. And that's what you see. In the beginning, they won't grow very fast, because there are not too many bacteria, and the more bacteria there are, the faster they grow. So after a lag, what we call a lag phase, we have exponential growth. Well, and the growth reaches a maximum just at the moment the food is used up. And then the biomass concentration decreases because they die, these microorganisms. So that's basically the process we have. And of course, in practice, in a continuous process like this one, we like to keep the microorganisms at a maximum growth. Yeah? Because that's the basics of the activated sludge process. So concentrating the bacteria, because basically it's the same process as takes place in rivers. If you load wastewater, discharge wastewater to a river, the bacteria that are in this natural system will break down the organic material, of course. But the concentration of these bacteria is very low. And that's what we do in such a system. That's by recycling the bacteria, so settle them, yeah? Settle them and feed back to the reactor. That's a way of artificially increasing the bacteria concentration so that we can treat more water in a small volume. We don't need a big lake or a big river. But in fact, it's a natural process, but it's engineered. So typical values of sludge concentration in this reactor is about, what's the number? 3 to 5, that's true. Yeah, it's more 3 than 5, or 4 grams per liter. Expressed, again, not in grams bacteria, but in grams sludge. Yeah, and we talk about suspended solids. That's the organic material that's swimming around in the reactor. Okay. Yeah, so important is the settleability, because if it doesn't settle, so these flocks of bacteria, they come in the settler, in the sedimentation tank, and they need to settle. Otherwise, they will be washed out, and we will lose them. And of course, they won't contribute to a clean effluent. They grow, because we feed them with wastewater, so they grow. And the growth is about 0.8 to 1 kilogram of dry suspended material per kilograms of BUD converted. So the BUD, again, that's the kilograms of organic material per cubic meter, unit of volume, that's loaded to this reactor. And this BUD is converted by the bacteria, it's eaten, and because as a result they grow. But of course we feed back a big part of the sludge, but there's also a net growth, and at some point we will have too much sludge in the system. That's why we have a discharge of sludge. That's the sludge production. And that's a fact of waste. And you can consider this as a concentrated form of the problem. The problem is polluted wastewater, organic material in the wastewater, and in fact it's concentrated in this waste sludge. And this is wasted. There are different ways to deal with that. We'll come back to that. But it's called waste sludge. The sludge age. That's the average time that bacteria, these microorganisms, stay in the system. And that's in the order of days. It can be up to 25 days. So the higher the sludge age, the older the sludge is, the more possibly specialized bacteria are in the system, which can be very helpful. And it's important to realize that the sludge age, or the sludge retention time in days, is different from the hydraulic retention time. The hydraulic retention time is just the throughput through the system. The hydraulic retention time, that's in the order of hours. And the sludge retention time in the order of days. That's because we can separate water and sludge. Clear so far? So you'll realize that in order to keep a good sludge balance in the system, that this return line is very important. In fact, if you do a mass balance over the settling tank, this is what we feed back. That's the flow of the return sludge times the sludge concentration. So that's kilogram of sludge per unit of time. That equals what's flowing into the settling tank. Yeah? And that's here. That's Q plus QR. Because, let's use this. If this is QR, return flow, and Q is the influent flow, then of course this is Q plus QR, right? So we forget about this for the moment. Yeah? So for a sludge balance, then we just look at this input and this output. Well, okay, so then QR times XR should be the sum of these two flows times X. And X is the concentration in this reactor. Well, this gives a way of calculating the required return flow to obtain a certain concentration of biomass in the aeration tank. Because remember, we talked about the sludge load. Yeah? And for the sludge load, it's important to know how much sludge is in the system. Kilograms of suspended solids per cubic meter. So that's X, in fact. So in order to keep a certain sludge load, a certain X in the aeration tank, we need to control the return flow. And that's a way to calculate the return flow. Yeah, this is just a different way of looking at it. And yeah, it's a bit fiddling around with symbols. But what's important here, that's another term, and that's the SVI, Sludge Volume Index. What's the sludge volume index? If you take a sample, that's also explained in the next slide, this one here. If you take a sample of sludge, the color is brownish, grayish of real activated sludge. It's not black, it's not this color, but it's a bit in between gray and brown. Anyway, so if you fill a beaker or a cylinder of 1 liter with this sludge and then wait 30 minutes, what will happen? Exactly what will happen here. It will settle. And after 30 minutes, you've got a small volume of sludge. This is, in fact, clear. Yeah? This is clear water, and the urea, the sludge, the activated sludge. So and the sludge volume index is this volume divided by the concentration of sludge. And, well, in this case it's called suspended solid, mixed liquor suspended solid, which means that we talk about the suspended solids in the mixed liquor. And the mixed liquor, that is this liquor, this content of the aeration tank. So in fact, again, we just divide this volume by the concentration of sludge in the tank. So, and then we obtain the sludge volume index. And it's expressed in milliliters per gram of sludge. And this is an important variable because it shows how good the sludge in fact settles. And it's expressed in gram because if you have a lot of sludge, it won't settle volumes, of course. That's why we express this in a relative way per unit of volume. Okay, well, when this is smaller than 100, typically 50 milligrams per gram of sludge, then we say it's good settleable sludge. Settleability is good. If it's not, well, you might have similar problems in the settling tank. It won't settle very good. And then it will be washed out. There's risk that it will be washed out. And again, we need to keep the sludge in the system. We need to recycle it in order to increase the concentration in the aeration tank. So we need small SVIs. So, and that's why the SVI comes back, I'm now going back to the previous one, in looking at the maximum attainable sludge concentration in the return line. Because you realize that the concentration XR in the return line depends on how well it settles. Yeah? So the value of the sludge volume index. All right? Okay, so if we want to build a treatment plant, and yeah, so usually this is wastewater coming from a factory or a city. Wastewater. It's a certain amount in terms of volume, so cubic meter per times of unit of time, cubic meter per hour, cubic meter per day. How much wastewater do we produce as a person? What do you think? Is it 10 liters or 100 liters or 1,000 liters per day? 100, yeah. It's a bit more than 100 liters per day. And in fact, that's the water we use, the drinking water. And this is comparable to the wastewater we produce. There's a bit, of course, because in reality, if it rains, and in the Netherlands we have these combined systems, the rain is also added to the wastewater, which will dilute the wastewater. So it's not just the volume of wastewater, it's also the concentration, which is important. So that's why we talk about the FM ratio, so the sludge load. We look at kilograms of BUD that is coming into the system, and the system will be designed based on the amount of BUD to treat, but also the flow in terms, the hydraulic flow, in terms of cubic meter of water per unit of time. That's also important because especially the biology is dependent on how much BUD or CUD we have to treat, but especially the settling systems, so the settling tanks, they are critically dependent on also the biomass that's grown, especially here for this one for the solids in the wastewater, but also the volume of wastewater flow. Okay, so, well, we select a biological load. I explained that if we want to have BUD removal, it's usually higher loaded. If we also need to oxidize nitrogen, which is the case in the Netherlands and all over the world actually, well, not all over the world, in Europe, then we need to keep lower loadings. So it's dependent on the type of treatment we want to achieve. Well, we calculate the required aeration volumes, of course, the required volumes of the settling tanks with maximum load. We need to calculate the return sludge concentration, also the flow, how much we have to discharge of excess sludge, but also very important, oxygen requirement. I already explained that this activated sludge uses oxygen. You have to aerate. The problem with oxygen is that only 8%, 8 milligrams of oxygen per liter can dissolve in water, which is not much. Which means that if you aerate water, it will quickly disappear, because especially if what we want, high concentrations of microorganisms, these use a lot of oxygen, and the oxygen will be depleted in no time. So that's why we need to aerate. I already mentioned that this is 75% of the energy costs of a wastewater treatment plant. So you really need to aerate a lot. So it's very important to have a very well-designed aeration system. I'll show some pictures of this aeration system. So we have a break, but I'll take 10 minutes more if you agree, just to catch up with the time we lost. Yeah, this is just, again, a general picture of a treatment plant. And yeah, it's more or less a summary. And as you can see, the S, it means concentration of BUD or CUD. Both are measures of the concentration of pollutants in the wastewater. And they will decrease, of course, because of the primary settling. They will decrease even much more in the aeration tank because of the conversion, the oxidation by the bacteria. And also we will settle material here. And we will produce waste sludge, which is mainly consists of bacteria, and we produce primary sludge, which is garbage. That's just all that settles in sewage. And again, to summarize, if we just look at the biological system, so if we forget for a moment about the primary settling, so the sludge load, well, this is L, but you also see B. Bx is the flow times concentration divided by volume of the aeration tank and the sludge concentration in the aeration tank. Sludge load, important parameter. And of course the efficiency, because yeah, once we have a treatment plant, we want to know how, if it's doing a good job. And yeah, okay, that can be expressed in concentration at the influent here, minus concentration at the effluent, divided by concentration at the influent. So what do you think in terms of COD? What will be the efficiency? It's in percentage. Is it 100%? It's not 100%. Is it 1%? It should be a bit more. 50, 60, 70, 80? Yeah, 80, 90. Would it be, do you know the difference between BOD and COD? Not yet. BOD, that's biological oxygen demand. So that's the amount of oxygen you would need if you oxidize the pollutants in the wastewater. The chemical oxygen demand is the amount of oxygen if you would oxidize the pollutants chemically. Not by using bacteria, but chemical oxidizers. Which would be highest for the same water? Because a chemical oxidation is more powerful. And it also sometimes wastewater, if it's from a industry treating or producing chemical compounds that are not degradable, it will still have a high COD. Because chemically you can oxidize this material, but biologically not. That's why the BUD is always lower. So also in terms of efficiency, because of the BUD will be degradable and the COD not fully degradable, the efficiency in terms of BUD is always higher than the efficiency in terms of COD. Yeah? Agreed? But 80, 90%, that's typical for activated sludge plants. This is the volatile fraction of the sludge. Yeah, I mentioned the concentration of sludge, the concentration of bacteria. It's impossible to measure bacteria. At least it's a big challenge. So we express the concentration of bacteria in terms of suspended solids. And that's what we call mixed liquor suspended solids. But if we measure these solids, by filtration, for example, and then burn this material, when we dry it and burn it, then what will be volatile is in most cases the organic material. And what remains are salts, for example. Yeah? So if we express this concentration in terms of volatile suspended solids, then we're closer to the organic material, which is most likely bacteria. Yeah? Is that clear? So that's why the VSS is closer measure of bacteria concentration than SS, which will be larger. The VSS or TSS. It's the total. suspended solids, because this includes salts, for example, minerals. Yeah? And the volatile suspended solids, that's only the organic material that disappears when you burn it. And the ashes remain. Yeah? So this fraction is always smaller than 1. And typically it's 75%. 70% also possible. There's a few more parameters. That's a recirculation factor. Well, I don't need to explain that anymore. That's the fraction of the return sludge flow compared to the influent flow. Return sludge concentration. That's the sludge concentration expressed in mixed liquor suspended solids or mixed liquor volatile suspended solids. But this can be calculated, of course, based just on mass balancing. Remember, we did a small mass balance a few slides ago, and in that case we didn't consider this waste sludge. And of course that's not completely correct. In fact, if we mass balance, we have to deal with sludge coming in to this this settler, and that's, well, this line, but there's in fact 3 points where sludge leaves the system, and that's the waste sludge, that's the return sludge, and that's the sludge that's sneaking out through the effluent. Because I mentioned that we need to settle this sludge. But in fact, we're not doing a completely perfect job in this case. There will always be some material, some bacteria that swim out of the system through the effluent. So and we also have to deal with that as well. But of course, we like to keep it as low as possible. Okay, back. Just I missed one. That was the sludge production. So this one is related to the net sludge we produce by wasting material from the system, the activated sludge. So and also this is a matter of mass balancing. So this is expressed in kilograms of sludge per unit of time, logically. And this sludge production comes back in an equation where we express the kilograms of sludge that has developed based on compared to the kilograms of sludge of material of COD we have converted. So this is interesting to know, because if you know for the design how much kilograms of BUD or COD you are feeding into the treatment plant, you have to, on beforehand, to be able to calculate the sludge production and the yield. So you need the yield, how much sludge you would produce per kilograms of COD converted. That's important to design, for example, the sludge waste pumps and so on. If we had time, I would ask you to calculate this value, and you can try it at home, to calculate this value based on this equation. So what's that equation? This is a general formula of biomass, bacteria. So bacteria, organic material, consists of carbon, hydrogen, nitrogen, and oxygen. Of course, there's more. There's also a lot of minerals that is converted to ashes if you burn sludge. But this is a good approximation of the sludge of the formula of sludge, of bacteria. So if you oxidize it using oxygen, you would get carbon dioxide, of course, ammonia, and water. And if you know this, you will be able to calculate how much oxygen you need to burn in kilograms of biomass. And burning, that's oxidizing, and that's the same as biological oxidation, because it's all expressed in terms of oxygen. Which means that now we are able to express not only the pollutants in kilograms of BUD or kilograms of CUD, and better kilograms of CUD basically, but also the sludge in terms of kilogram CUD. Because kilograms of CUD, chemical oxygen demand, is exactly the amount of oxygen we need to convert 1 unit of biomass. And this is very important because this makes it, well, enables you to express mass balances of this system in terms of CUD. And CUD is expressed in oxygen, and oxygen, that's electrons. So in fact, you're doing an electron balance. And you cannot get rid of electrons. You cannot make electrons. So a mass balance can be closed if you express influent concentrations of organic material and sludge as well in terms of CUD. And that's what we mean with this value here. Is that clear? More or less? Yeah, that was the last one. This is also an important one. That's the sludge aged. I mentioned it already. And, well, if you have the volume, multiply the volume of the aeration tank with the sludge concentration in the aeration tank, you get the amount of sludge, kilograms of sludge. And if you divide this by sludge production, kilograms of sludge produced per day, you will get a value expressed in days. That's obvious, of course, but it means that this is the average time a sludge particle, one bacteria, stays in the system. It grows, it grows up, and then it's wasted through the wasteline. So, and that's the average time the sludge has stayed in the system, and that's the sludge age. And the older the sludge is, the more specialists can grow to, for example, to convert particular pollutants. Yeah, this is a bit about sludge wasting. Well, you can read it again in the syllabus or in the handouts, which will be published today. Yeah, I mentioned that already. So approximately this waste stream in terms of flow is about 2% of the influent flow. So if we have 100 of cubic meters per hour, we have 2 cubic meters per hour of waste sludge, which is still a problem to deal with, of course. It's a concentrated problem. Yeah. Oxygen consumption. A very important, well, the microorganisms will consume oxygen, as explained, and you will have to supply oxygen through aeration. So there will be an oxygen consumption. And the oxygenation capacity, that's in fact the OC, that's in fact the capacity of the aeration system to bring oxygen in the system. So we need high values for that, of course, and efficient equipment to do this. So that's the amount of oxygen per unit of time, defined by the amount of oxygen per unit of time in clean water. And unfortunately, in activated sludge, it's less. It's easier to dissolve oxygen in clean water than, unfortunately. And that's expressed with this alpha factor. And also the capacity is multiplied with another fraction, and that's the saturation concentration of oxygen, which is about 9, 8, 9. And the actual concentration. So if the actual concentration equals the saturation concentration. Suppose the saturation concentration is 8. That's maximum concentration of oxygen that can dissolve. If it's 8, then yeah, it's the same, and this term is 0, which means that the actual capacity is 0. And that's true, because the amount of oxygen that you can bring into the system depends on the fusion of oxygen from an oxygen bubble to the liquid. And if this is already saturated with 8 milligrams per liter, you cannot add more oxygen to the system. So the actual capacity is 0. The capacity is maximum when? When would you have a maximum capacity? So a maximum diffusion of oxygen from the air bubble to the liquid. Exactly, when it's 0. So when this is 0, term is 1. So we cannot go higher. That's the best capacity we have. But still, of course, we have this alpha, which is smaller than 1, but that's because of, there's particles in so this is not only liquid, there's also sludge particles sitting around, and they disturb the diffusion process of oxygen. Aeration systems. So we have a few types. I'll go through them. So this is a point aerator, an example. And this is a rotor. Well, this is just, I'll have a more detailed picture of that. This is the rotor, a point aerator. And it's just a motor and a kind of, what would you call this? A rotor that makes a high revolution speed, and that brings the water. It's a fast mixer, in fact, like a food processor. So it brings a lot of air in the water. It's also, of course, mixing the system as well. They use a lot of energy, by the way. These seem to be a bit more efficient. That's a rotor aeration. This is if this is a cross section of an aeration tank, it's a big rotor that's turning on the surface of the aeration tank. So and then it's making this revolution. And there are brushes or all kinds of materials which brings the oxygen, the air, in the water. It's a bit more efficient, and it also mixes and transports the water in a big aeration tank. Disc aerators, like in a fish aquarium, it's these diffusers, porous material that's sitting on the bottom of the aeration tank, and air is pushed under high pressure through these systems. By the way, if you happen, and that will be part of this course, visit a treatment plant, you will see these aeration tanks, and there's a lot of bubbles. And it happened, and I know this place where the operator, two operators, in fact, they had there was a bird was floating in the middle of the aeration tank, and they took a boat, a rowing boat, with two big guys in the rowing boat. It was in the United States, I remember, and they put this boat on the water, and then they got in, and then they immediately sunk to the bottom. And why was that? Yeah, the hold up. Exactly, yeah, a hold up. So if you have this aeration tank, and it's filled with water, this way, and if you start to aerate, especially using these diffusers, start to aerate, you will see that the level goes up. And it's not because there's more water, but that's because of the hold up of air, which means that the specific density of the water is much lower. And you all know what will happen then if you are too heavy with this small boat. So it's very dangerous. You cannot swim in an aeration tank when it's aerated. So don't try. Yeah, so you can, there are several types of disc aerators, as you can imagine. And, well, mainly there's a lot of research still going on because these aerators, especially these disc aerators, these diffusers, tend to clog. Bacteria grow in these small holes. And the smaller the bubble, the better, of course. The better the transfer of oxygen to the liquid. Positioning of aerators, that can be just in a part of the aeration tank to create a kind of flow. Ridge and furrow, this is the furrow, this is the ridge, to create a particular, a more detailed flow pattern in the aeration tank. And the bottom, the floor aeration, which is very uniform over the whole aeration tank. Aeration tank can be rectangular, but it can also have a long shape in order to create plug flow type of flow. Yeah, positioning of aerators. There's a lot of different options here, and sometimes we don't want to. That will be in the next lecture. We don't want to aerate because we want to create certain processes, and then we need to mix. Then we also introduce mixers, because the aeration itself is ideal for mixing. It's an expensive mixer, but it's ideal mixer. The efficiency, I already mentioned that this is expressed in the OC, and that there's a difference between clean water and activated sludge. Yeah, so by aeration you can induce mixing. And, well, this is a bird view of a treatment system. That's what you can recognize if you are on a plane. They're very visible, usually, these treatment plants, and mainly because of these big settling tanks. Yeah, different kinds of mixing. That's a lot of details. This is an example of a carousel. It's a kind of ditch. So the wastewater enters here, and then it goes all the way in a plug type of system, and it comes back. But it's more or less simulating a river, but it has a different properties in terms of performance. Two-stage activated sludge process. Just quickly, you can have two different systems which are in series, and the wastewater is coming in system, and of course this is high loaded, and of the pollutants are already removed when it enters the second step, the B step, and in this way we create different kinds of processes, and the sludge that grows in this system is different from the sludge that grows in that system. And one of the reasons to do this is to that it's easier to make sludge with good settling properties. Okay, well, this is I'm now going a little bit quickly through this presentation in order to have some break. But also I mentioned already a number of things like the SVI, sludge volume index, which determines how much sludge you can concentrate it in the settled material. Yeah, sure. Yeah, I was also, but there's another, let me just see how much, because it's almost done. I can use a break as well. Yeah, okay, let's break, and then I have a few notes to finish this, and because most of it is pictures, and then we will continue with nitrogen and phosphorus removal. Agreed? Okay, let's break 10 minutes. Yeah? Okay. Okay, so let's finish this. I just wanted to add that this secondary settling tank, it, as already suggested more or less in this drawing, there's a kind of storage of sludge, because sludge settles and it's pumped back to the aeration tank, but there's a certain amount of sludge that's sitting and waiting in this settling tank. And this provides an opportunity because you can imagine if during rain events we have a higher hydraulic flow, for example, if this is increased and we keep the same here, the same flow here, then the concentration in the aeration tank will be diluted. So we can use this by increasing the return sludge flow in cases of rain events. So, for example, we can keep these two in a certain ratio, 1 to 1. Yeah? So if this is 8 grams per liter, this is 0 grams per liter, almost, then this will be 4, the result. If we increase this flow, we need to increase this flow as well to keep the same concentration here. So then we make use of the sludge stored in the settling tank. And that's the basic message of this slide. And it all depends, of course, on the maximum concentration we can reach in, where's my stick? Oh. That we can reach in the settling tank. So we need this sludge volume index. Another important parameter of the settling tank, and that's related to, as I already mentioned, the hydraulic throughput. So it's not only the concentration we can reach here, but it's also the throughput expressed in the term V0, the surface loading rate here, which is in fact the Q divided by the area, cross-sectional area of the aeration tank, the settling tank. So this has a certain area, and the amount of the volume that can go through this settling tank divided by the area is the V0, the surface loading rate, which is also a very important parameter of this settling tank. Okay, so that's all related to that. This is a few pictures of settling tanks. I already mentioned they're pretty big compared to the rest of the treatment plant, and they take a lot of space. And that's usually a problem in urban areas. Okay, that's all. This is an example, a cross-section of a typical circular settling tank. This is a scraper, which can also be recognized in pictures. It's revolving, so it's a kind of bridge, but this is revolving typically every 20 minutes. It makes one tour, 20 minutes, 30 minutes. And it scrapes the sludge that's settling on the bottom to a ditch from where it's pumped to back to the aeration tank. And yeah, that's a nice anecdote. This is a measure of the activity of the biomass of the return sludge. You can measure activities, for example, by measuring oxygen utilization rates. But anyway, they discovered a very interesting phenomenon, this periodic change of the activity of the sludge. And, well, they spent some time on it, and they couldn't figure out what was going on. And then, yeah, there was eventually somebody smart enough to realize that the period of this change